Hello Intensified Bio students. So this video tutorial is to help you analyze your raw data, to help you make sense of it so that you can put your data into a summative data table and then make some nice graphs and then analyze your data with descriptive and inferential statistics. So the first thing you have to do is go to Canvas and you have to download the Excel workbook, and this Excel workbook is called 9th Grade Practice Using Excel. And you also have to download the Word document, and the Word document is also in Excel, and it's called Practice Tables, Graphs, and Statistics for Science Fair. So once you've downloaded these two documents, there's a nice little trick that allows you to have both documents open at the same time. So if you click on this green button here and you hold it, it allows you to split your screen and have both documents open at the same time. So it also says that you should watch this video lesson that I prepared for you before you go ahead and you complete this assignment. So number one, it says to go to sheet 1, and remember that on Excel you can open different sheets with this plus tab, and every sheet is given a different number. So sheet 1 is open here, and sheet 1 is showing you raw data for height of plants in centimeters over a 30-day span. So this data is mock data that we can use to help you analyze it. So the first question, it says, look at the numbers of the data collected. Does the rounding match? So I've highlighted a few numbers here on the raw data in yellow, and you tell me, do you think that these numbers match with their rounding? So notice that some numbers are rounded to the 10th of a place, some are rounded to the 100th of a place, and some are rounded to just one digit, like the 6 and the 7. So if you're measuring height of plants in centimeters, you probably used a ruler, and you probably cannot get more precise than the 10th of a place. So probably saying that you collected data to the 100th of a place might not be very accurate, or even to the 1,000th of a place. That's probably not very accurate either. So you want to make sure, it's just proper notation, that all of the data you collected is all rounded to the same place. And in this case, since you're measuring height of plants with a ruler, probably to the 10th of a place would be a good place to round. So Excel can do this rounding for you with one easy step. So the first thing you have to do is highlight all of your data. And right here I've added these blue boxes that give you instructions in case you forgot how to do certain things. So I'm reminding you here that you can use the shift arrow down or the shift arrow up key, or the shift arrow left or right key to highlight your cells. And also remember that with a Mac, in order to right click, you must right click with 2 fingers, and a drop down button tab will open like so. So let's go up here and let's highlight all of our raw data to make sure that we can now round all of our digits to the same place. So as you highlight, make sure you're highlighting everything like so, and then make sure you right click inside the highlighted area. So when you right click, a drop down button appears. You're going to scroll down to Format Cells, and you're going to click on Category Number, and then the sample shows you what your number will look like if it's rounded to 2 decimal places. So remember that you want to round to 1 decimal place. So you're going to say 1 decimal place here, and in the sample it tells you what your numbers will look like. So you're going to hit OK. And notice that in one easy click, you fixed all of your numerical data. Everything is now rounded to the 10th of a place. Okay? So now you can answer questions 1 and 2 here on the Word document. Question 3 is asking you if you see any outliers in experimental group 1. So here you have experimental group 1, and here I have the definition of an outlier. An outlier is a numerical value that differs greatly from the group or trend, and an outlier might represent a mistrial or error. So if you go back to experimental group 1 here, do you see any numerical outliers? So I'll let you look for a moment and see if you catch a mistake there. So look at this data point here. So this is telling you that plant number 5 at day 20 had a height of 6 centimeters. And then at day 25, your plant had a height of 4 centimeters. And then on day 30, your plant had a height of 9.8. So there's obviously something wrong here, right? You can't really go from being 6 centimeters tall and then shrinking to 4 centimeters and then going back up to 9.8 centimeters. So that probably means that this number, 4 centimeters, was an outlier. Okay? So what do you do with outliers? Well, you can take them out. You can delete them out so they don't count if you're not 100% sure that they were indeed a mistake that you made. You can leave them. So it's up to you what you want to do with that outlier. Here you see another outlier, right? You see the height of plant number 2 after 30 days. It really just grew a lot, right? It went from 6.2 to 18. And notice that no other plant grew that tall. So this might be a mistake, this might be a fluke, this might be an error in your measuring. Again, it's something that you're going to want to explore before taking out that outlier. Okay? So you can now answer question number 3. So question number 4 is asking you to use the raw data and calculate descriptive statistics such as the mean and standard deviation. So that's what we mean by descriptive statistics. So the mean is the same thing as the average, and the standard deviation is the spread of values above and below the mean. So a high standard deviation means that you have high variability around your mean. So that means that your results were pretty much all over the place, right? There were results that were above the mean and there were results that were below the mean. A low standard deviation means low variability. That means that all of your results were somewhere around the mean. So then that tells you that if you have a high standard deviation, you probably have low precision because your data was all over the place. And you might have low accuracy as well. And a low standard deviation means that you have high precision because all of your measurements were very close to the mean. Okay. So for question number 4, you are going to calculate the mean and the standard deviation for every group, for groups 1, 2, 3, and 4, and then you are going to, and also for the control, and then you're going to write it down here on your Word document. So let me show you how to do that. So if you go up here to these red boxes, I give you Excel formulas. So it says that the mean can be calculated by highlighting all the values of each group. And the Excel formula for the mean is equal, average, and then you input your data within the parentheses. So all of your highlighted cell values will be found within the parentheses. So before you do that, it's a good idea to set up a summative data table. So your summative data table, all it's going to have is your mean and your standard deviation for your control group and your other 4 groups, and that's pretty much it. So notice the difference between a summative data table, where all you are showing me is the mean and the standard deviation, and notice the difference with a raw data table that shows me every single measurement you took every single day throughout your whole experiment. So for your results, you are supposed to show me both. You are supposed to show me a summative data table, and you are supposed to show me a raw data table. So this summative data table is going to be set up like so. And here I have already some of the results. So let me delete those before we move on. And we are going to do this again. So let's look at your mean height. So what would be the mean height of your control? So your control is this group right here. So to calculate the mean height of the control, you have two options. You can do the mean height of all your measurements taken for all 30 days of all 5 plants, and you can take the average of everything. Or depending on what you're trying to investigate and what your hypothesis tells you, you can just find out what the mean of each plant was after a 30-day growth. But for the purposes of this tutorial, I'm just going to show you how to calculate the mean of everything for the control group. So in the box under control, I'm going to type in the formula in Excel. Now it's very important that you type in the equal sign because that's how Excel is able to identify that you are putting a formula and that you are telling it to do a mathematical computation. So instead of typing mean, you're going to type the word average. And average is the same thing as the mean. So when you click on average here, notice that 2 parentheses open here. So you're going to input your data within those parentheses. So you're going to go back to your control data and you're going to highlight everything. Remember, shift down and right. Okay. And notice that when you do that, Excel automatically puts in the cell numbers for each box. So then all you have to do is hit return and it calculates the mean for you. So instead of having to input all of these numbers in a calculator one by one, Excel has calculated the mean for all 5 plants over a period of 30 days. Again, depending on what you're investigating, you could have done the mean of all 5 plants at the end of the experiment, at the end of 30 days. But again, that's up to you and whatever you're investigating. So I'm going to go ahead and calculate the mean for all my groups. So now I will go and calculate the mean for experimental group 1. And notice that I am not highlighting the days because the days are just days, are not the growth of my plant. So make sure that when you're highlighting your cells, you're highlighting the appropriate cells. So when I hit return, I have my mean for experimental 1. And remember that you can always pause this video and go back and see how I did this. And you can also pause the video while you yourselves are calculating the mean here. So let's do experimental group 3. And make sure you're always highlighting the correct data because it's easy to get confused with so many numbers. And experimental group 4. And, oops, I forgot to type in the formula. Experimental group 4. I highlight all the data again. And there it is. So now I have my mean for all of my groups. So this is how tall each group of plants grew over a period of 30 days. Also notice that my title is descriptive and I have the unit of measurement here. Notice that all of my numerical data is rounded to the 10th of a place as well. So for standard deviation, here in the red box, I tell you that standard deviation is calculated by highlighting all values of each group and that the Excel formula is equal STDEV, that stands for standard deviation, and then you put your values in parentheses. So you're going to do the same thing that you did for mean, but now you're going to do it for standard deviation. So you're going to hit equal, STDEV, and make sure you're hitting the correct formula. There's many different types of standard deviation calculations. The one that you want is just your standard deviation, STDEV. So you're going to hit on that, and again, the parentheses opens. You're going to go back to your data. You're going to highlight all of your numerical data, and you're going to hit enter, and that calculates your standard deviation for this group. You're going to do the same thing for experimental group 1. Standard deviation, highlight all of your data, and you hit enter. For experimental 2, standard deviation, you highlight all of your data, and you hit enter. For experimental group 3, standard deviation, highlight all of your data, and again hit enter. And experimental group 4, standard deviation, highlight all of your data, and again hit enter. So now you've calculated the mean and the standard deviation for your groups. And before we go ahead and we graph anything, let's just try to make sense of what these numbers are telling us. This tells us that our control group that had a mean height of 3.8, we'd had growth that was up to 2.27 above the mean, or growth that was an average of 2.27 below the mean. So this standard deviation here is showing great variability in the measurements for the control group. But even more variability, because you have a higher standard deviation, you see more variability in your data collected for experimental group 1. For experimental group 2, you have a lower standard deviation, even lower for experimental group 3, and very low variability for experimental group 4. So these are aspects of your descriptive statistics that you can talk about in your results. So now you have your data, and you have your summative data in a nice table. What are you going to do with that? So if you go back to the Word document, you can now answer questions 5 through, I guess, 10 already. And for 10, it says that you need to paste the data table in the space below. So we've done this before, but remember that when you take your whole data table, you gotta highlight it, and you right click, and you're gonna copy that, and then you're gonna go to your Word document, and you're gonna paste your data table in your Word document. Okay, we had some difficulties there, some technical difficulties with the spinning wheel, but we got it fixed now, so we can continue. So you're in the process of copying your summative data table and transferring that to your Word document, which is important because once you have all of your data tables and graphs prepared in Excel, you're going to need to transfer those to your paper, which is going to be written in Word. Remember, you're doing that in Word and not Google Docs, because Google Docs tends to distort the graphs and the tables. So I recommend that you use Word. So again, your summative data table is highlighted. You are going to right click on your highlighted area, and then the drop down menu appears, and you're going to go to copy, and then you're going to copy that in the Word document. So you will go to your Word document, and again right click and paste, and now your summative data table has pasted in the Word document. Notice that it doesn't look like a table, so you're going to have to make some adjustments. And when you copied it, before you click on anything, make sure that you have this clipboard here, because this clipboard is going to allow you to actually fix the design of your table. So when you click on the clipboard here, another drop-down menu appears, and you're going to want to hit match destination table style because that's what's going to make your table actually look like a table. I've told you in class that if you have really big tables that might get distorted or that might not fit in your Word document, that you can also paste this picture. The only problem when you paste this picture is that you can't do any modifications to the table itself. So for now, we're going to hit match destination table style. And notice that now it's a picture. So in order to modify, it's now a table. So in order to modify this table, I am going to make this document bigger. Okay. And make sure you highlight your whole table, and you highlight it by clicking on this little cross sign here. And notice that you now have these two tabs that open up. One is called Table Design, and you can fix your shading and border style of your table, and then the other one is Layout. So in Layout, you can now fix rows that you don't need. So for example, this row here you no longer need. So you can go to Delete and delete the whole row, and that gets rid of that row. And then if you want to delete certain lines, you can hit on the eraser. And then if you want to delete a certain line, like so, right, you just hit that line that you want to delete, and the eraser deletes that. To get rid of the eraser, just click in the document somewhere, and that gets rid of the eraser. And then you can make this table, as big or as wide as you want it to be by dragging it here up and down. Okay, so now you have your summative data table, and you can also make adjustments to your title, whatever else you need to do. So question 11 now says that you should take the information in your summary data table and construct a bar graph with standard deviation error bars. So let's go back to the Excel document, and let's open up both documents at the same time. Actually, I'll just open the Excel document right now so you can see better. So now we're going to take the information that we have in the summative data table, and we are going to make a graph. And it says here, place the graph here below, and then cut and paste it into your Word document. So in order to make a graph, you need to highlight whatever it is that you are going to graph. And in this case, you are going to graph your control groups and your experimental groups. So notice that I highlight that information, and then I go to Insert, and I want to insert a graph. So I scroll here to either recommended charts. It'll show you what the charts look like, or just a bar graph. But here I just realized I made a mistake because I highlighted standard deviation, and you don't want to highlight that. So again, you just highlight your mean height for the control for experimental 1, 2, 3, and 4. You do not highlight standard deviation. Standard deviation is going to serve for error bars to show the variability around the mean. So once you highlight your mean height of all groups, go to Insert and insert your bar graph like so. So notice that now you have a pretty little graph here that you can move around wherever you want. You can make it as big as you want it, and now you can modify certain things of the graph. Okay, so notice that each bar has a name, right? Control experimental 1, 2, 3, and 4. But notice that the title is not appropriate. Your title should be more descriptive than that. We practiced that at the beginning of the year. So here's the mean height of plants. So make sure you change that, and make sure you add the unit of measurement, centimeters, over a 30-day span. Okay. But also notice that you are missing the X and the X title, right? So what does the, I'm sorry, missing the Y title. And this is your vertical value axes. So how are you going to fix that? So highlight your graph, and then notice that these tabs open up, chart design and format, and you're going to add a chart element. So when you click on add chart element, you are going to add a title. And in this case, you want to add the primary vertical title, and this is what where you're going to be able to include what the y-axis represents. And in this particular experiment, the y-axis represents the mean height, and it's always important to include the unit as well in centimeters. So now you have a graph that has a proper title, all of your groups are labeled, and your y-axis is labeled as well. So now you're missing error bars. So the error bars are important because they give you a visual. They give you a visual that represents standard deviation. So in order to add your error bars, you are going to highlight the bars themselves. So again, let me show you how I did that. So if you just want to highlight the bars themselves, you click on the bar, any bar. Let me do that again. You click on any bar and notice that these dots appear surrounding the bars. Okay. So when you highlight the bars, you now have these tabs, chart design and format, and you can now add your standard deviation error bars. So you go to chart design, and then under add chart element, you scroll down to error bars. And you are not going to add the obvious standard deviation error bars. You would think it's that, but it's not. You are going to go to more error bar options because you are going to standardize your actual values. You have to input them manually, because notice that in your summative data table, your standard deviation differs per group. So you will go to more error bar options, and now you have a right panel appear. And notice that it adds some error bars here, but obviously they're wrong, so you can't keep those. So you're going to go down and customize your standard deviation error bars, and you are going to specify a value. So now this window opens up, and your positive error value is your values that are above the mean, and your negative error value is the values that are below the mean. But they both represent the standard deviation for each group. So you're going to click inside the parentheses here. You're going to delete the number 1, and you are going to add your custom error bars. So you are going to type in your standard deviation first for your control, 2.27, and then the comma is going to tell Excel that now you want the error bar for experimental 1 group. So you're going to type in your standard deviation, 3.57, comma, 0.49, that's for experimental 2, comma, 0.25, comma, 0.08. So now you have your positive error bar, and your negative error bar is going to be the same. So delete the number 1 and type in your standard deviation again, 2.27, comma, 3.57, comma, 0.49, comma, and 0.25, comma, and 0.08. Now, some of you might be wondering why your standard deviation is to the 100th of a place, and if you should change that to the 10th of a place, and the answer is no, because it is standard practice to leave your standard deviation to the 100th of a place. Okay, so once you've typed in your standard deviation values, you can just hit OK, and notice that now your standard deviation error bars look different. So now I'm going to close this panel, and I'm going to make my graph a lot bigger, and now you can see clearly how the standard deviation error bars differ. Okay. Now let's analyze what this is telling you about your results. So here you have for experimental 1 a very large error bar. That means that even though your mean was somewhere around 4 what was it exactly? Let's see. Even though your mean was somewhere around actually 3.57, I'm sorry, 4.7. Your errors, you have an error that could be all the way down here, okay, to a little bit above 1, or you can have an error that could be all the way above here, a little bit above 8. So all of that is your possible error. That means that you were all over the place in collecting data here for experimental 1 group. And the same thing for the control, right? You have a very large error bar. And remember what I told you before, that large standard deviation represents very low precision. So large standard deviation is equivalent to having very large error bars. So now when you can visualize these error bars, you can now make some descriptive statistic analysis, which means, well, this error bar for my control group overlaps with this error bar in this control group. So my results between my control and my experimental 1 group are not statistically significant. That means that my results could have been as low as 1.2, and there is an overlap with my control here. So there is not a big difference in my results between my control and my experimental group 1, right? But if you notice the other groups here, experimental group 2 and experimental group 3, there is a slight overlap, right, in the error bars, but not too much. And experimental group 4, you could definitely see a difference here. Whatever you were doing to experimental group 4, it had a significant effect on that group. So the plants here did not grow as much. So in comparing experimental group 4 to experimental group 3, there is an obvious difference. And we call that a statistical difference. So there is a difference between 4 and 3, there is a difference between 4 and 2, and a difference between experimental groups 4 and 1 and the control group. So just by looking at my error bars, I can see that my independent variable, whatever I added to my 4 different experimental groups, had an effect in my plant growth. And that's what we call descriptive statistics. The error bars are allowing me to visually see if there is a difference in my groups based on my error bars and based on my standard deviation. Okay, so let me make this a little bit smaller now. And now I have my graph, and it says here that you are to cut and paste your graph to your Word document. So you can adjust your graph to make it look nice and pretty, and you can cut it. And then if you go to your Word document here, you can paste it here under number 11. Okay. So here we go, and hopefully this doesn't freeze. And there it is. So now you have a nice graph, and it's in a Word document. Okay. So now you can answer questions 11, 12, right? You can see that the error bars tell you standard deviation, and they tell you, you can see if they overlap and they don't overlap. So if the error bars overlap, that means that there is no significant difference between the groups. If the error bars do not overlap, like experimental 4 and 1, you can see that there is a significant difference between those groups, right? So by looking at these descriptive statistics based on the error bars, would you accept or reject your null hypothesis? So remember that your null hypothesis says that your independent variable is not having an effect on your dependent variable. by looking at this graph here, it is obvious that the independent variable was having an effect. So by just looking at the error bars, I can say that I can reject my null hypothesis. There is an effect. There is a change happening here, right? So now you can answer up to question 14. But just looking at error bars doesn't give me any numerical certainty. So this is where inferential statistics become important. And this is where we're going to take it up a notch and we're going to take it to a different level. So for question 15, it says that you must activate your analysis tool pack on Excel, and this is in the form of an add-in. And this is going to allow you to calculate either an ANOVA test or a t-test, depending on what you're doing, in order to calculate a p-value. And your p-value is a statistical number that with certainty can tell you if your results are statistically significant or not. So in other words, is your independent variable having an effect on your dependent variable? And by looking at this p-value, if your p-value is less than 0.05, that means that with a 95% certainty you can say that your results are statistically different and that you can reject your null hypothesis. So I am going to show you how to do that now. So let's go back to sheet 1. We're still in sheet 1. And let's analyze the, let's put the graph back here. And let's analyze our results with inferential statistics. So here in case you didn't get everything I just said, here in the blue box I wrote down the difference between descriptive statistics and inferential statistics. So here you are in Excel, and go to the very upper banner here, and you're going to want to add in the form of Excel add-ins the analysis tool pack. So go under Tools and then go to Excel add-ins, and this box appears. So you're going to want to click on Analysis Tool Pack because you will need that to conduct your statistical analysis. So press OK. All right, and once you do that, when you click on Data here, you now have this tool here called Data Analysis, and that's what's going to allow you to do an ANOVA test. Okay, so an ANOVA test is very helpful when you are comparing more than two groups. So instead of having to individually calculate p-values for every group one at a time, the ANOVA test calculates the statistical significance of all groups at the same time. So an ANOVA test is used when we're trying to find a statistical difference between more than two groups. So let's go back to our raw data table because we're going to have to highlight everything in our raw data table. So click on Data, and then click on Data Analysis, and then all of the different statistical analysis tools are available here. So the first one that you need is the ANOVA single factor, and that's all we're going to worry about right now in the 9th grade. So you're going to do an ANOVA single factor, so you're going to hit OK, and your input range is the range of all of your raw data. So you're going to highlight all of your raw data once again. Okay. So here's all of your raw data highlighted, and notice that I am not highlighting the days. I am not highlighting anything that's non-numerical. I am only highlighting data. So I am grouping by columns because, again, the way that I've set up my raw data is in the form of columns. If you set up in the form of rows, then you're going to have to switch that to rows. But here I have all of my groups in the form of columns. So I'm grouping by column. My alpha is 0.05. This is my p-value that is going to denote statistical significance. significance, and then I want my results in a new sheet. So I will hit OK. And that opens a new sheet, notice right here, sheet number 4, with all of my statistical analysis. So there's a lot of numbers here, right? It tells you that it analyzed 35 data points in your 5 columns, and it again does the average for you. And then these are the results of the ANOVA test. You don't have to worry about what everything means here, but degrees of freedom, just to make sure that you're analyzing correctly, is the number of groups minus 1. So here you have 5 groups, minus 1 gives you 4 degrees of freedom, but the number that you're concerned for and the number that you want is this p-value right here. And this p-value says 0.98. So when looking at this number here, this is saying that there is no statistical significance, right? Because you were supposed to have a number that was less than 0.05 to be statistically significant. So then what does that mean? If we go back to our results here, it means that because you had so many overlaps in error bars, right? The control group overlapped with this one, and it overlapped with this one, and it overlapped with this one. You can't really say that there was too much of a difference of the independent variable on the dependent variable. So here's an example of how, when you're looking at the error bars, you're right, you might think that there was an effect, but then your statistical analysis says that there isn't, right? Because your p-value is such a high number. But you might still question and say, well, what about between experimental 3 and 4? They obviously look different, right? What about between 4 and 1 and 4 in the control? They obviously look different. So here's where you can do what we call a t-test. So if you just want to analyze to see if there is a statistical difference between just 2 groups, you can go ahead and conduct a t-test. So how do you do that? Well, I want to see if there's a difference between experimental 4 and experimental 3. So let me go back to my raw data here, and doing a t-test is much easier than doing an ANOVA. So the formula for t-test is just equal t dot test. So Excel does that for you. And inside these columns, I am going to input the data for experimental, what did I say I wanted to see? Experimental 4 that look completely different. And then I'm going to hit comma, and then I'm going to compare that with experimental group 1, let's say. Okay, and I'm going to enter. And, oh, sorry. And I'm not going to enter yet because I also need to do comma 2, which is my two-tailed test. I'm doing a two-tailed t-test. And that tells me that my p-value, notice, is my p-value for a t-test is very, very small. It's 9.26 times 10 to the negative 11. That is very small, okay? So what did my inferential statistics tell me here? It told me that, if we go back to sheet number 4, it told me that I have a p-value of 0.98 when conducting an ANOVA test, when looking at all groups. But it told me that I have a p-value of, if I go back to sheet 1, of 9.2 times 10 to the 11th. My p-value here is 9.2 exponent 11. That is less than 0.05. So then I can say that there is no statistical difference between all of my groups, but I can say that there is a statistical difference between groups 4 and 1. And sometimes your analysis might vary like this. And if you look at your graph, let's go back to sheet 1. If you look at your graph is in agreement with your statistical analysis, right? So between the control and all of these groups here, there is no statistical significance because there is an overlap of error bars. But just between experimental group 4 and experimental group 1, since there is no overlap, then I can say there is a statistical significant difference between experimentals 1 and 4. And you can go ahead and do a t-test between 4 and 3 and 4 and 2 and see if there's a difference between those two. But the ANOVA test is just simply saying that in the whole experiment, you cannot be certain that that independent variable that you added to each group indeed had a statistical significant difference. Okay, so now we're going to continue with our Word document number 16, and it says to go to sheet 2. So in sheet 2, we have two different data tables. Data table 1 is comparing the size of the zone of inhibition in two bacterial populations, and data table 2 is comparing the solubility of tablet pills in minutes in different pH solutions. So let's look at the questions here in the red box. So which inferential statistic test will you conduct? For data table 1, would you run a t-test or an ANOVA test? And for data table 2, would you run a t-test or an ANOVA test, or maybe both? So down here in this blue box, I've given you definitions of the ANOVA test and of the t-test. And just like we did in the previous examples, we conduct an ANOVA test when we have more than 3 groups. So it allows us to determine if the independent variable is having an effect on the dependent variable. And if we calculate a p-value that's less than 0.05, then my results or your results are statistically significant, meaning that they are different, meaning that the IV is having an effect, and you can reject your null hypothesis. But if your p-value is greater than 0.05, then your results are not statistically significant, meaning that your independent variable is not having an effect, and your null hypothesis has to be accepted in this case. Same thing for a t-test, but the only difference here is that a t-test is conducted when you're comparing 2 groups alone. So up here, notice that you have 2 groups. So it makes sense to run a t-test and a t-test alone. So question number 16 is asking, what is the p-value for the t-test, and are your results statistically significantly different? And when in your data is it appropriate to conduct a t-test? So let's run a t-test, and remember that to run a t-test, the formula in Excel is equal t-test, and then you are going to highlight experimental group 1, or your first group. Then it is important to add a comma to separate it from the other group, and you're going to highlight the other group, and then you're going to add a comma again, and then you are going to type in the number 2, comma, and the number 2 again. That means that you're running a two-tailed t-test between 2 groups, and Excel recognizes that as the correct formula. When you hit enter, it gives you a p-value here of 0.925. So is that statistically significant? And the answer is no, because it is greater than the p-value of 0.05. So now let's look at what else can you do in data table 1. Well, you can also calculate mean. So if you remember, in order to calculate mean, I take the average of my data points, and I do that for my other one as well. So those of you who are only comparing 2 experimental groups, this is something that you would do. And if I want to calculate standard deviation, I type in the formula in Excel, and I highlight my trials, make sure that I'm highlighting them correctly here, and I do that here as well. Okay, and you can fix your rounding here to the 100th of a place again by formatting your cells. Right click, format cells, and I want my standard deviation to be to 2 decimal places or the 100th of a place. And now that is properly noted there. Now for data table 2, I have more than one group. So for number 18, what do you think you would do? Would you do an ANOVA test or a t-test? So since you have more than 2 groups, an ANOVA test is needed. So in order to conduct an ANOVA test, remember you have to use your data analysis up here on the right-hand corner. So you're going to have to click Data, Data Analysis. You're going to do an ANOVA single factor. You're going to hit OK. And make sure that your input range is highlighting only your data. So whatever you have for your control group, whatever you have in your other groups, and you are comparing again columns with an alpha of 0.05, and you want your results in another sheet. When you hit OK, that's going to open sheet number 5 here with my ANOVA results. And again, 4 degrees of freedom because I'm comparing 5 groups. And look at my p-value this time. My p-value is 6.2. And again, be careful here because it's not just 6.2, but it's 6.2 exponent negative 37. So that is a very, very small number. So that value is, of course, less than 0.05. 6.25 exponent negative 37. So that is a very, very small number. So for my data table 2, all of these results are statistically different. They are statistically significant because my p-value is less than 0.05. And you can go ahead and calculate the mean and the average for all your groups, okay? Which of course these are a form of descriptive statistics, and I'm not going to do it for all of them just for time's sake, okay? So now that you've learned about using Excel to calculate mean, standard deviation, graphs with error bars, the ANOVA and t-test, can you do the same with your science fair results? Because pretty much this is what you're going to be doing with your own results. And what challenges do you face with your own data? So if your data is not set up the same way, what are some of the challenges that you face? Of course, I am here after school. The science fair mentors are always available to help, and you can email me with questions. So if you are not doing an experiment where you have to correlate data, you can stop watching right now. But if you are doing an experiment where a correlation analysis is needed, a Pearson R is needed, then continue watching. So go to sheet 3 for number 20, and under sheet 3 I tell you what correlation is. It's a statistical measure that calculates the strength of the relationship between the relative movement of 2 variables. So for example, is the increase in the levels of carbon dioxide having an effect on the global temperature, for example? So a Pearson's correlation coefficient is also known as a Pearson's R, can be calculated to study if there is a correlation. And a correlation is studied between values of 0 and 1. So nothing can be greater than 1 or negative 1, or nothing can be less than negative 1. So when we calculate a Pearson's R, a -1 is going to show as a perfect negative correlation, and a value of 1 is going to show as a perfect positive correlation. A correlation of R of 0 shows that there's no relationship between the movement of the two variables. So something important when doing correlation to remember that correlation doesn't always imply causation, right? So the example that I give you here is if I break out with pimples every time I eat chocolate, can I then say that my pimples are being caused by the chocolate? Well, maybe not. What if the pimples are being caused by some other effect that you're not measuring here? That is a hormonal effect. What if the hormonal effect is making you eat more chocolate and you then break out in pimples? So correlation doesn't always imply causation, and that's something that you have to keep in mind when doing a correlation analysis. So you can answer A, B, and C, A and B here, right? And now let's actually go ahead and calculate a correlation. So for data table 1, I give you two variables. So for the two variables, you can calculate mean and standard deviation, but they're just descriptive here, right? Because the value that you are interested in is correlation. So to calculate correlation, the formula is equal correl, which stands for correlation, and then you're going to highlight your variable A and your variable B. So let's type in the Excel formula, equals correl. So you're going to click on correlation, and then a parentheses opens. You're going to highlight variable A. There it is. And then you're going to do a comma to separate it from variable B, comma. Okay, you're going to now press enter, and now you have a Pearson's R of 0.92. So remember what I told you. I said that a correlation of 1 shows a perfect positive correlation, right? So we see a value here that's close to 1, so we know that we have a positive correlation here. For data table 2, let's do the same thing. Let's calculate correlation coefficient, equal correl, and let's highlight the variables above. All right, so let's continue. We had some technical difficulties here. So I'm calculating the correlation coefficient again. So correlation of that first group highlighted, comma, versus that other group highlighted, comma. So that gives me a correlation coefficient of 0.1. So it's still a positive correlation, but it's not as strong correlation because it's not close to the value of 1. So let's try to visualize that with graphs. So how would you do a graph that shows you a correlation? So what type of graph do you think you would need? So you have many different graphs here. Would you do a line graph, a bar graph, or a scatter graph? So of course a scatter plot would be the correct graph for showing a correlation. So in order to insert a graph, go to Insert, Scatter Plot Graph, okay? But you're going to want to highlight your data first. So highlight my data, and I am going to insert a scatter plot graph, like so. So here it is, and it is showing the relationship between variable A and variable B. Of course, you're going to have to put in a proper title, and you're going to have to add your labels for the y-axis and the x-axis like I showed you before in the other tutorials. The other thing that is useful in a scatter plot is to be able to insert a trend line. So you can do that by going to adding chart elements and add a linear trend line to see better what's happening. So this is like a line best fit. And you can see that there's a definite positive correlation here, right? So you see the line is going up. So that's what the graph for data table 1 would look like. Now let's look at the graph for data table 2. So again, I'm going to highlight my variables, and I'm going to go to Insert, and I'm going to insert a scatter plot graph. And notice how my data points are everywhere, right? So there is a very weak positive correlation here. And by showing a trend line, going to add chart element and adding a linear trend line, you can see here that the line is almost flat, right? And remember that being at a correlation of 0 means that there is no correlation whatsoever. So here you have a correlation of 0.1, so it's not 0, but it is a very weak positive correlation, okay? So this is how you do correlation. So you can now answer all of the questions right here for 20 and 21. Save this document and upload it to your Canvas assignment, and you will be done. Thanks for watching.